Why on earth would we ever want to run a regression? I can think of a couple of particular reasons. First, I think, what if we're interested just for our research, not just if there's a statistically significant difference in a sample, like the goodness of fit example that I just showed you, or a more complex understanding of the directionality and significance of the relationship between two particular variables, like an x and an y, than a simple correlation like the Pearson's correlation coefficient, which we've also talked about. This kind of pushes us towards more sophisticated analysis, but one that taps into a similar kind of effort at trying to look at the distances between what a particular value is from a predicted average value. So here, just using this screenshot from one of my statistics textbooks, you see this graph, which we've seen a bunch of different times over the course of the term, in which you have two variables. We're assuming here that they're continuous variables that we care about. The outcome is the y, and the predictor, or the thing that's affecting our outcome that we are focusing on, which is the x. And so here there's a positive relationship, right? That the common example that statistics textbooks and YouTube videos that I've seen talk about is the difference between height and weight. So people who are taller on average are expected to weigh more. And what you see is these different observations don't all perfectly fit on this regression line, right? That you have this this one dot here, like an example observation 3, that is at a lower than expected value for y, this difference here, than the predicted value there, and you see the value x is there, right? Let's see. And so for regression, what we're trying to do is we're just trying to find one particular line, right? There's a whole bunch of different lines that we could follow. Actually, all the lines should go through the mean values of these two different variables. So let's say this is x hat here, and this is y hat here. That through these average values for these two variables, there are a whole bunch of different lines that you can draw. And so what you're trying to do is you're trying to choose a line that is minimizing the distance between all these observations to the expected value. And see, you can see here, you also have this derivation here from y2 here to the expected value of there. And so what you're trying to do is you're trying to draw a line in which these values are the smallest possible, right? And in order to do that, you use this particular formula, which hopefully you'll see similarities with to the Pearson's correlation coefficient, standard deviations, etc. That you have two statistics here in a basic bivariate ordinary least squares regression. That is a mouthful, but you see the least squares estimators here is we're trying to estimate beta hat. That is the slope of the line between your x and your y, and the alpha here, which is the intercept. So if you have, I don't want to draw my head. So you have this relationship here, and so you have your x and your y, and you have the line here. Then the slope here is the beta, the slope. And then the alpha here is the value when x equals to 0. And that's just a linear transformation here of the basic regression, just moving y over to the other side of the equation. So y equals alpha plus bx, and what you do is you just keep y there, and you're just moving bx over to the other side. Right? So that is the basic formula for the beta and for the alpha, and you can see the calculations for the average values for the x and y down at the bottom there. And so with those statistics, that gives you an estimate for that slope of the line and where the line crosses zero. And with that, you have the basics for much more complicated models. But let's walk before we can run. And so I thought I would do another example in Excel in which we can have data here from the related to the Hibbs article for the number of industrial strikes taken from the International Labor Organization, unemployment rates for these countries, so 45 countries in the available sample unemployment rate. Polity will be the third variable, which we're not going to see this week, but I'm just interested to see whether as unemployment goes up, the number of strikes goes up. And so my observable hypothesis would be as unemployment goes up, the expected number of strikes will increase. Okay, the null hypothesis is that there is no relationship between unemployment rate and strikes. As unemployment rate changes, strikes don't change significantly. So with that, let's go ahead and get out of the slides for now. And I have this handy dandy Excel spreadsheet in which I have the values. Let's see, the raw values here. When you have the different countries, strikes, and unemployment rate, you can come up, as with any data, I would encourage you to get to know the individual variables and conduct descriptive statistics. Here, just in the interest of saving time, I created this summary histogram of strikes in 2016. So you see the vast majority of countries have very few strikes. There's a few countries that have an incredibly high number of strikes. If you go ahead and look at the numbers of strikes here, you see Brazil here would be the outlier with the highest number of strikes, 2,227 in our sample. You have a couple of others like Germany that has a large number of strikes, but then you have other countries like Estonia that have no strikes. So this gives a bit of a visual description of the nature of the data. I also use the technique that we've already covered in a few weeks ago in the class to use the Excel data analytics tool pack to create summary statistics. The mean number of strikes in the data are almost 150. Standard error of 57. The median value is strikes. Median value of strikes is 15, which hopefully should tell us, given what we've talked about earlier today, that there is this right skew, that you have a few number of observations at a high number, a number of strikes. Then you have some with 0. The mode indeed is 0. The most common category is no strikes. Most common value is no strikes, while the median is 15. So there's a lot of gap between these two. The variance, kurtosis, skewness, the range goes from 0 to 2127, and the minimum and maximum, right? There's 45 different values. So these are a couple of initial descriptive statistics I always like to do before I move on to other more complex analysis. I also did a quick scatter plot of the dependent and independent variables. Hint, the students are writing papers in my class. All these statistics are ones in which would be completely justified to include it in your final essays. Means, distributions, talking about the difference between the means and the modes, looking at the bar charts there, or scatter plots here, looking at the independent and dependent variables. Here we see here the x variable is the unemployment rate on the x-axis, and the outcome we're interested in explaining is the strikes in the y. And I highlighted a couple of influential observations here in which you had a country that had high unemployment but lower than expected amount of strikes. Here's a linear prediction here in red. And you had Germany with a higher than expected number of strikes given the lower unemployment rate. And you have Brazil here as a clear outlier, Argentina and Spain as well. Again, this moves from just descriptive statistics about one variable to an initial kind of first cut analysis of the relationship between these two variables. You can also run a correlation, which I didn't actually do as well. But here you had this regression overview from the slides here, and you also see these the distribution of the variables. Let's see what this actually looks like to calculate. Let's see if I can do it by hand and then match it to this Excel generated value. I'm not sure I can, the pressure is mounting. First, what we want to do is just look at the equations here and create columns for each one of these different elements. It reduces the chance of making mistakes, and it helps you catch the errors, like unfortunately the ones from last time had. So first I'm looking at the y bar or y hat and x hat here, which is the average values for each one of these columns. So I have the equation here. You can see it. All you do is just remove the quote and puts it here. So you see the average number of strikes is 150.2. I do the also the case for unemployment. Average unemployment rate is 16.1. And then you look here, this one is the second part of the top of the beta hat equation, y minus y hat, or y minus y bar. And you see, oh, forgot the equals there. And so you see, if you look at Argentina here, the number of strikes was 1321. That was 1,170 strikes more than you would expect given the average value of 150. So you calculate that for each one of our different observations. You see some are above the average and some are below. Austria only had 11 strikes, which is below the expected value or had 0 strikes, which is 150 less than the average value. Need to put the equal sign in front of these. That tells Excel that that's an equation. See unemployment rate here. Argentina had an unemployment rate of 22%, which is 5.7% higher than the average of 16%. And then now we can have the product of these two for each one of the different variables. So that is 5.7 times 1,170. Bring that down. And then now we're going to do the denominator, which is the difference between the observed values of x and the average. Drag that down so you have all those different values. And now what we need to do, because you see to calculate the slope coefficient, you have to sum all those different values for all 45 of the different observations. So kind of like here at the bottom, we had average values for the x and the y. Here we're summing these two different columns. Hopefully by doing this via video, you can pause it, go back and replay it to try to understand these different steps. And so here we have the sum for the numerator and then for the denominator of your beta. And then all you have to do to get the slope coefficient is divide that by that, which I have the formula here. And then you get a slope coefficient of 11.29, which you can actually interpret as being a 1 unit increase in of an unemployment rate. As the unemployment rate goes up 1%, the expected number of strikes would go up by 11. So there'd be 11 more strikes for 1 unit increase, 1% increase in unemployment rate. With ordinary least squares, you can directly interpret the coefficients as a 1 unit change in the x variable, and given gives the expected change in the dependent variable. Not as clear cut with other forms of regression with variables that are like 0, 1. Is there a civil war or not? And so now we're interested in getting that alpha, which is where the line crosses 0. What would be the expected number of strikes here for in a country with absolutely no unemployment? And that gives a value that is actually negative, because every country has some form of unemployment. You really don't see any values here that have 0, and so that's why it actually gives a negative value. And so that is a quick and simple and abbreviated version for how to run a regression. You can do it by hand. We'll be practicing this in tutorial, not this week, but in the future. There are other statistics and determining whether these coefficients are statistically significant, connecting to our discussion earlier today with a tabular analysis and with correlations. That is to come. I just wanted to highlight the basics for actually how you run and determine the slope of the line that minimizes this distance between the observed values and the average values. And then, so let's double check our numbers and make sure I didn't make any clear mistakes by going to the analytics tool pack in Excel that we added in several weeks ago. So we go to data analysis, and we're going to go down to regression, click OK, and we're going to input our dependent variable range and independent variable range. I already pre-populated from when I did this before. So from cell C2 to C47, anytime you put a dollar sign there, like in these equations, it helps keep, it doesn't change the value if you drag it to a different cell. We're going to do labels and output it right here. And we're going to have a residual plot, which shows the difference between the expected values, like I showed earlier, and the observed values. And let's do that there. Let's move this over here. And so you see a regression coefficient for unemployment of 11.029, which matches that for the beta hat. And the value, which is they call the intercept, but it's the alpha hat, the value when unemployment equals to 0 of negative 27.908. So I had that a bit wrong, but I'll consider it a win for the time of night that it is now. And you see a whole bunch of other statistics, like the R squared here, which shows how much of the variance in the number of strikes is explained by our model. Right now it's a bit under 8%. We're gonna talk about that in a second. But that is how you run a regression in Excel manually. And then you can do it with your Excel, Stata R, whatever statistical package that you have that it makes the most sense. So that is a brief introduction to how to do it manually. Let's go back to my slides. I wanted to just briefly connect the correlation coefficient and R squared to kind of show that there is the direct relationship between what we've already done and what we just did today. The Pearson's correlation coefficient is just used to identify patterns between variables. How closely are they related? How much dispersion is there in that relationship between them? The coefficient of determination r squared that we just saw in the regression equation is used to identify the strength of the model, how much the variation is explained. It's not a variable I'm really a fan of, which we'll get to the reasons why in a bit later. But I just wanted to highlight the relationship between what we've already seen and where we're going with regression. A couple of quick takeaways now, and we'll end for today. First, ordinary least squares is about fitting a line that minimizes the squared distance between the sample values and the line. The reason why it's squared, I don't think I've mentioned this earlier, is because if you just did a line and you didn't square it, then the derivations that for the line that you would choose, by the definition of what the line you would choose, the derivations above the line would be offset by the ones above it, and you'd end up getting a distance, a sum distance of 0. And what you want to do is square the distance so that those two reach an absolute value. This regression gives us two important estimates. First, the slope of a line, summarizing the relationship between your x and y variable, and then the expected value of your outcome when your variable of interest here, x or unemployment, is equal to 0. And the intuition behind how it's calculated, the fact that it's trying to draw the line that minimizes the square difference between the average, the predicted value, and the actual observed values, helps us understand what this regression can and cannot tell us. It doesn't tell us anything about causality. It doesn't tell us anything about the quality of the data. What it is another measure of a correlative relationship between these values. Connected back to the motivating questions for today, we're trying to understand how we can try to not lie to ourselves and others with statistics by understanding the assumptions of the models that we use and understanding the data that we have. We talked about basic probabilities, how they're used to understand most of political science research, that we have estimates that we, descriptive or causal inferences that we estimate, right, with a correlation coefficient, the tabular goodness of fit analysis or regression analysis. But basic probabilities help us determine whether that sample mean, whether that estimate of the beta is due to chance or to an underlying relationship that is you can be 95% and 99% certain is not due to chance. And then how can we understand several different types of hypothesis tests? I introduced two today, the tabular goodness of fit test and the ordinary least squares regression. The OLS regression is a workhorse of modern political science and a whole bunch of other different fields. It is that kind of touchstone in which all other models derivate from for a specific reason, either causal or because most directly the nature of the data that we have and how they violate the assumptions of the regression equation that I just showed you. With that, thank you for your time. I hope you found this useful. Feel free to play it back again. Oftentimes it takes multiple times to really get at the intuition, but that's what I'm really trying to hammer, that you have statistics and then probabilities as to whether those statistics are due to chance or underlying relationship. That is the fundamental common thread between all these things that we've looked at so far in the quantitative analysis of this course. And hopefully that'll hold you in good stead when you try to generate these data or to be able to understand why other people use them as well and whether they do it well or not. With that, thank you for your time, and I will see you next time. Thanks.